Okay, so let's start. So we are just resuming the reading group, and today I'm going to talk about some results in online learning. So very shortly, yes, just to sum up a bit the talk. First, I will try to motivate a bit the talk and to justify why typically complexity is important in online learning. What is it and what it is and so on. Then I will present some results in convex learning, so some very general results for algorithms in convex learning and in randomized learning, so Bayesian favored algorithms. And finally, how it is possible to go beyond complexity. So in the same, I will present a recent result of a recent paper that went out last year. So first, the references. So typically, the first reference is a book from Cherief-Abdellatif and Badr-Eddine. So it is very general and it contains results in online learning. So the second one, I mean, the three following are like kind of between books and tutorials. So the first one is quite short. It's a kind of an introduction to the topic. So with a lot of intuition and motivation if you're interested in the topic. So the book of Hassan is, and as well as the one of Rabban are good references. You can find a lot of results in it and with proofs and a lot of things. And the last one is just a paper that just was, so it's still a preprint on the archive that went out, I think, in November, October last year. So it will be the last focus on the talk. So of course, if you have any question, please interrupt me. So first, so just to fix the setup. So let's, for instance, consider a classification framework. So this is just an example. You can generalize it to regression and even to non-supervised learning. It doesn't really matter. But just what is online learning? The online learning deals with streaming data, actually, and streaming and online decision making, actually. So just imagine the case where you're given, let's say, for instance, an image. Okay, so you're given an image, which can be either, this is a digit, for instance, and it can be either a 0 and a 1. And you're asked whether you think it is a 0 or it is a 1. So first, you're not prepared to the task and you're not given any examples. So maybe at first, your guess will not be very good. So you will say, okay, I think it is whether a 0 or a 1. So here, x1 is an image that is given to me, and y1 is the true answer, 0 or 1, and y1 hat, sorry, is my guess. So after my guess, I have the true answer. So the true answer is y1. So y1 is revealed. And then, next step, I am given a new image. Okay, so it is an image of a 0 or 1. And then, given my experience and whether I was wrong or right previously, I can like correct my guess and adapt my guess, have a new guess for this new image, have the true answer, and so on. So I have a new image. I need to give a new guess, and I have a new answer, and so on. And the goal, actually, in online learning, the objective is to learn well as fast as possible. So as fast as possible, I want to make good predictions. And to the question, what means predict well? Typically, if I fix a time horizon, capital T, what I want to be able to do is to make as many mistakes as possible. So if I just count the whole number of mistakes that I make up to time T, and this for any time, any horizon T, I want to do only a few mistakes. So this is the objective. And the particularity of online learning, one of the particularities when compared to standard predictive machine learning, is that in general, we do not make specific stochastic assumptions on the data. So we typically do not assume that the data are specifically IID, so independent, with the same distribution. We do not make such assumptions. So typically in the case I choose, in the example I choose the images, so there is an underlying data generating process, but this is not necessary actually. And the question is, what can we expect in general? And so, as I just told you, we do not make any assumption, but if you do not make any assumption at all, of course, this will be infeasible. So let us just, for instance, consider, so once again, the case of classification. So the thing I have to classify is either a 0 or a 1. And the loss I suffered is the 0, 1 loss. So whether I am right or wrong, okay? And if I do not make any assumption of the data at all, so it will be very, very difficult, because if you just remember, the answer is given after my guess. So typically, if I make no assumption of the data, it is possible that I have like an adversary in front of me, and when I just make a guess, the adversary say, okay, I choose the opposite answer. So in this case, at each step, we are sure to fail, actually. And so I wrote it like a result, but it's like quite obvious. With no assumption at all, you cannot do better than a fail at each step. So typically, this just shows that we need to make some assumptions on the data. So actually, covers impossibility result is a bit more complex than this. So I just sum up a bit like that, but it's very related to this idea, actually, and it's stated in Cherief-Abdellatif's tutorial that I just presented in the introduction. But yeah, you can find this result, which is formulated as a regret bound, actually. And so the question is, what kind of assumption should we make, actually, or can be made in order to get some interesting results? So to do so, I will take the opposite case in a way where you have, you know that there is a true underlying data generating process. So you know that there is a true relationship between the input, the image X, and the answer Y, okay? And you know that such a relationship exists, but you do not know which one it is. So you just have a model, a collection of functions, of predictors, so F1 until Fm. So we suppose that we have like the number of predictors that we have in the model is finite. And we know that one of the predictors is the good one, so never fails, but we do not know which one. And the question is, how is it possible to control the number of mistakes that we make? And if the answer is yes, how can we design a learning algorithm that is able to control this? So the algorithm that's a very naive algorithm and basic algorithm that can work is actually what is called in Cherief-Abdellatif the consistent algorithm. And the idea is very simple. To say that at first step, I do not know at all which predictor is the good one. I know that there is one, but I don't know which one. So I pick the first one, okay? And I just make a guess using the first predictor, so F1 of X1. Well, X1 is the first image. And I just see at the end of the step, when the true answer is revealed, which of the predictors were right and which were wrong. So all the predictors that were wrong, I know that they are not the good one. They are not the oracle that is always right. So typically, I can move them out. So I have kind of an admissible set of functions that are candidates to be the oracle. So at each step, actually, I remove candidates, the predictors that failed at the previous step. Okay, and then I have an admissible set. So if I was right, my function, my current function, my previous function is still a candidate. So I still take this one as the next predictor. And if not, I just take the first candidate in the remaining set of admissible in the admissible set. Yeah. So typically, the algorithm can be summed up like that. So I am given an image. I take, so the choice is the first choice in the admissible set, and I observe the true answer, and I update the admissible set so that the only the predictors I have at the next step will be the one that never failed, that have been consistent with the predictions at all previous steps, okay? So, and what is a guarantee that we can have with this algorithm, actually, it's that the number of mistakes, the total number of mistakes I made is at most linear in the number of predictors. So it is quite easy to see, because each time I make a mistake, I know that at least one predictor will be removed from the set. So after after m mistakes, I know that after m minus 1 mistakes, I know that will be just one predictor in the set, and I know that it is the record, so I'm done. And basically, so is it the best we can do? And yes, the answer is yes. Just imagine that we have like m predictors. So all right, but the first one at step 1. At step 2, all right, but the second. At step 3, all right, but the third one. So it means that at each step I will be wrong, and I will pick the next one that will be wrong at the next round. So typically, I cannot really do better than that with this strategy. So the question is there a strategy that can do better than that with the same problem, exactly the same problem? And with exactly the same scenario, actually it is possible to design an algorithm very easily that makes better than this one with just changing one thing, which is the way I predict, I choose the predictor. So I still keep an admissible set. I update the admissible set in the same way. It means that I just rule out every wrong predictor at round C, but I just change one thing, which is the way I choose my predictor. And the answer is it's a very simple choice. It's just not to take the first one as my choice. It is to consider a majority vote. If I do this, I just say, okay, it's not, so to begin with, I don't take the first predictor in the set as my predictor. I just ask their opinion to every predictor. And if there is a majority of 0, I pick 0. And if there is a majority of 1, I pick 1. And why is it better? Very easily, the reason is just that every time I make a mistake, it's not only one predictor, at least one predictor that I rule out, is at least half of the predictor. So either I am right, in which case I don't know which is the general behavior, either I am wrong, in which case I rule out at least half of the predictors. And so like that, instead of ruling out one at each step, I rule out half of the predictors at each step. And instead of obtaining a linear bound on the number of mistakes, I obtain a logarithmic bound on my predictor. So there is almost no change, you can see. Thus, so the name of the algorithm, which is called halving because we rule out half of the predictors. So just the way we choose the predictor, so it's not one specific choice, the first one, but a majority vote. And so the bound, which is much better, so logarithmic, two logarithmic bound on M. So this is, yeah, sorry.
Cannot it be that then after n steps, you never limit anything because you always have the majority correct? So you had more than n steps and still fully predict.
Can you just repeat?
So imagine that there are a few, like there is one which is always correct.
Okay.
But like you are kind of unlucky that you get. And so all the time, you always predict the correct result. Yeah. With the majority. So after m steps, you still have all the predictors that can be, because you keep just checking the majority. So you didn't remove any.
But I think this is m mistakes, not m steps.
M is the number of mistakes.
Here, no, M is the number of predictors in the set.
Oh, sorry, T mistakes, and not number of steps, right?
Capital T is number.
So capital T
is the number of steps is the total number of steps. I mean, is the horizon time, so it's the number of steps in my algorithm.
Okay.
Capital M is the number of. Okay.
But even in this, isn't the worst case still removing one at a time?
Sorry?
In this case also,
yeah.
Isn't the worst case still removing one model at a time, or one function from your set at a time?
But in the worst, you mean the worst case I presented previously?
No, in this case.
Yeah.
The worst scenario is that your majority is still correct, but you only have one function in your admissible set that is always wrong. So you're still removing one at a time. So won't your upper bound still be the same?
If the majority is correct, you will not.
Yeah, no. You always remove something. But if the majority is right, you just, I mean, each time, I mean, it doesn't really matter if the majority is right, because in this case, you do not suffer a mistake, actually. If the majority is right, you do not suffer a mistake. So it doesn't really matter to rule out only a few of them. And at the next step, if a majority is wrong, then okay, either it's a mistake for you, but you will rule out a lot of wrong predictors. So at the next step, you will not have a lot of.
So when the majority is correct, then you're not adding any penalty to loss.
No.
No.
Okay.
The loss is zero.
And what happens if, let's say, all of them are correct all the time? You don't have anything, so it's zero.
Yes, it's just a simple case with that.
But you also have the median.
It doesn't matter. That's not what we're trying to do actually.
So this is all assuming that your oracles in your decimals.
Yeah, this is
Yeah, so that is the assumption that
Yeah, this is a strong assumption, I know, but this is just really I said the extreme scenario.
Right.
So you have no assumption and a very strong assumption.
So sorry.
Yeah, sure.
So the goal is not that after your time horizon t, every prediction will be correct. No, it's just to control the loss after the time horizon.
Yeah.
Whatever after you make.
Yeah.
Okay.
Yeah. Yeah, so after this short example, so the question is, what is a realistic objective? Because it's probably somewhere in between. So we have the case of an adversary that want to mislead you, and the assumption that there is the existence of an oracle true model that you don't know, but you know the existence of a set which contains this one. So the probability, the real life is somewhere in between. And just the thing I wanted to highlight is, so not this specific situation, because it is really, the assumption is very strong, but in general, the second idea that we used and that gave us a good, a better bound at least. What is the idea behind? So we used aggregation. So majority votes, like the aggregation of all the votes of everyone. And actually, I just want to highlight the idea that hides behind this strategy, which is actually convexity. So this is actually the cornerstone in general of online learning. And just to try to give some insight on why it is important, just like, for instance, just think of what this aggregation strategy does. Actually, what we did is a majority vote. A majority vote is like the sum, just the sum, or the mean if you want, but so a weighted sum with equal weights of all the votes. Okay, so there is a 1, 1, 0. You make the sum, and you give an equal weight to everyone, and you compute the sum. So if the weighted sum is closer to 1 than to 0, you choose 1, and the opposite. And what you're doing at the next step when you're ruling out some of the predictors, actually, you just keep the first set of predictors, the initial one, but you put some weights equal to 0, and you just rearrange the remaining weights so that it's sum to 1, actually. So the idea is just to, in a way, to be able to compute a weighted sum with, and you're like optimizing the weights at each step so that you can like approach the optimal predictor. And so you can see this as kind of a randomization effect, okay, in a way. And imagine that instead of just computing the weighted sum, so the expectation, you just you choose, oh, sorry. You just choose randomly one of the predictor, but not the first one as we did in the consistent algorithm, but following the different weights that we have. If we do this, then what we have is a really random prediction y hat, which is equal to 1 with probability. So the probability is exactly the weighted sum, where pi t here. So pi t is the vector of all the sums. So at the beginning, it's a uniform vector. And the fxt here is just like the vector containing all the predictions. So f1 of xt, f2 of xt, and so on. So yt hat is a random vector, which probability of being equal to 1 is the weighted sum. And the question is actually, what is the expectation of what is the 0-1 loss between the true answer yt and our prediction yt hat? So as YT hat is random, you need to take the expectation, and the question is, what is the expectation equal to, actually? Because in expectation, what is the 0-1 loss between 1 and YT and YT hat equal to? Actually, it is equal to this. So the expectation of, once again, the 0-1 loss between YT and YT hat, which is highly non-convex problem, boils down to computing this, actually. And what you see is that if you see a problem as a problem of the expectation, I mean, if you see this loss as a function with respect to the expectation of your random prediction, you see that this boils down to a convex problem in a way. So because the expectation of YT hat of our random predictor belongs to 0-1, which is a convex set, and this is obviously, so the first quantity is obviously a convex function of the expectation. And if you see the problem not as a problem of just choosing a good single predictor, but of allocating the weights, what will you have? You see that the loss once again is equal to this, which is once again a convex problem because the probability weight belongs to the simplex, which is a convex set, and this loss is convex as well. So in a way, what you are doing is kind of convexifying the problem, actually. So this is just a small example to show that in general, what you can study is convex problems, because typically when you're considering a randomized strategy, you're convexifying the problem. So you can study directly the convex, because convexity is one of the key assumptions. So we'll just directly study convex situations and randomized algorithms as well. And so another point, which is what if the model is wrong, in the sense of the question you asked me. So previously we just computed just a number of mistakes, okay, which does not necessarily make sense. I mean, it made sense because the oracle doesn't make any mistake at all. But if you are comparing to something that can make mistakes, I mean, if you do not have access to an oracle, just considering the number of mistakes does not make sense in itself, and you need just to compete to something. So you need to compete against a competitor. And what we're interested in is the regret bound. So this quantity. And what is a regret? The regret is just the difference between your cumulative loss and this loss, which actually the regret in a way measures how sorry you are of not to have followed the predictions of the best predictor in hindsight. So this is what you're interested in. And what you want to have, so typically here you want to have something, so the regrets, so which is the difference between your cumulative loss and the cumulative loss of the best predictor in the hindsight, you expect this to be smaller than the total number of mistakes t. And so for instance, you expect something like a square root of t of the logarithm of t, something that is very small in front of t. Otherwise, you didn't win anything, right? So now I'm going to present some online convex optimization results. So it's again the same context. So the only difference here is that instead of just considering a prediction without specifying the way we predict, we make our guess, here we have like a set of functions, a parametric set of functions, and we just choose the parameter. So we choose the parameter that will make us choose our predictor, then we have the answer, and so on. We just update the parameter actually. So we do not update just a prediction, but we update a parameter. And the two things we ask is that the parameter set theta is convex, okay? So theta is the parameter of the prediction, the set of predictors, and the loss is a convex loss. So I just wrote LC of theta so that we can see that this is a function of theta. So we are interested of LT as a function of theta, but it just measures the difference, the loss, the distance in a way between our prediction f theta of xt and the true answer yt. So you can see that it is not restricted to actually to classification or even to supervised learning. And so maybe the most famous algorithm convex optimization is online gradient descent. So very quickly, because I think that most of you are familiar with this one. So you have a learning rate eta, you have a convex loss LT, you initialize your algorithm as θ1, and you compute the update. Theta t plus 1 is equal to this. So this is the only difference with standard gradient descent, is that you do not use mini batching or something like that, because we do not have access to a whole data set, but just at each step to one loss. And actually, I just want to just draw you to put your attention on this, which is another way of seeing the gradient algorithm that comes from exactly this. This is just another formulation of standard gradient descent. You can see it very easily if you just compute. This is quite famous, I think. And if you just derive this, you will exactly come back to the standard equation. And just a bit of motivation about this. Actually, so we just start from here, okay? So this is a bit like empirical risk minimization in a standard predictive machine learning. So this algorithm is called follow the leader, and you just pick the theta that minimize the cumulative loss at consider each previous step. And actually, the problem of this strategy is that in general it's not really stable. So one thing to do is to regularize this loss, so that we induce regularization, which is for a parameter theta squared Euclidean distance. And so we have something that is much more stabilized, and this optimization program is much better. I mean, it's a good prediction strategy in general. This strategy is very good in general, but the problem with this optimization strategy is that it's quite computationally expensive, due to the fact that if you want to compute to derive the gradient of this at each step, it means that you need to store all the previous data and to recompute the gradient at each step. And this is computationally quite expensive. So one way to avoid to do this, because the problem here is not the convexity, but the computational aspect, we just decide to linearize the first part. So this is mainly due to, it is more convenient from a computational aspect, but actually you exactly recover the online gradient descent. So this strategy is called follow the regularized leader, because you followed the leader, which is like the kind of the empirical risk minimizer. You regularized it, and in addition, you linearized it, at least the first part, and you get exactly this online gradient descent algorithm. So you have even another formulation of this, which is that instead of considering all the past losses, you just consider the last one, but you do not regularize with respect to the initialization, but just with respect to the last iterate. And the question, what kind of guarantees can we have when we consider online gradient descent with convex losses, with convex optimization in general? So we can get this kind of inequality. So actually, just a few words about that. This aggregate bound can be obtained in two ways, actually. It's why I presented the two aspects of the gradient descent, so like just gradient descent and follow the regularized leader, because the two, even if they are equal, the nature of the two strategies are different, and you have actually two different proofs to obtain the same result, actually. And what is nice is that you recover in the right-hand side almost the optimization program that you minimize actually at each step. Just the only difference was that in online gradient descent, this part is linearized. But this part, I mean, this is exactly, so your guarantee that you have is exactly the target, the objective you minimize, actually, which is quite nice. And so you will tell me, this is not really explicit because it depends on the learning rate, and you do not have an explicit dependence on T, given that actually you have kind of a penalization of this oracle with a squared Euclidean loss. So if you just want to have a regret bound in the formulation I gave previously, so with the only dependence in theta being here, you can actually, if you have a bounded set, so with a parameter with diameter d around θ1, you can have something like that. So you see that the regret, which is exactly equal to this minus this, is upper bounded by the sum of these two terms. And if you just like make a trade-off by tuning the learning rate, you can get exactly a bound in the square root of t. So what we have here is that whatever the losses that we choose, as soon as they are convex and Lipschitz, we can have a regret bound on our strategy, which scales as the square root of t, which is exactly much better than the t regret bound that t mistakes that we could have previously. So this is the general result that we have. And to the question, is it possible to do much better? So the answer is actually no, because what we know is that it is possible to find. So if you adopt, so whatever the strategy you adopt, there is a general situation, okay? So which is here. So this is for a specific choice of convex and Lipschitz losses, and for a specific vector, you know that you cannot do better than this, actually. So you see that the lower bound here is not exactly the same as the previous one, because the previous one just involved dl square root of t. So here it's a bit smaller, but in order, it's exactly the same, actually. So you cannot do better in order asymptotically as a function of t, but the result is exactly the same, actually. So you will have some situation if you adopt this strategy, you cannot get better than this square root of t bound. But you can do better if you add assumption. For instance, if you have like strong convexity, you can even do better, and so, right? So yes, it's what I wanted to say about convex online learning, and we'll shortly talk about Bayesian inference as well. So it's what we call in Bayesian inference, the posterior distribution is usually called exponentially weighted aggregation, so EWA. So it's exactly the same framework as previously. So you have a temperature parameter eta, you have the loss. So the temperature parameter in standard Bayesian inference is equal to 1. But here the goal is not to put it equal to 1, because it is as well a tuning parameter that will tune. The loss is in general the negative log likelihood in standard Bayesian inference, if you're more familiar with that. So you initialize, so pi1 in standard Bayesian inference is the prior distribution, once again, and you update you update your posterior distribution or your EWA distribution like that. So what you see is that actually it penalizes whenever you have a parameter theta such that at step t the loss is very large, then you know that the probability mass that will be given to this theta at step t plus 1 will be exponentially small in this loss. So if you have at step t LT of theta, which is very large, the mass that will be given to theta at step t plus 1 will be very, very small. So this is kind of the idea of this algorithm. And if you just, if you just formulate it, in another way, just like you iterate just in a general formulation as pt plus 1 as a function of pt, you just get, so I wrote pi here, it is pi1, sorry. And what you just get is that you just recover actually the standard posterior distribution if eta is equal to 1, if the loss here is a negative log likelihood. So pi t plus 1 is defined like that, it's EWA. And the question is, what do you have as a regret bound for that? So it is something, so I'm not sure it is formulated like that in the general case by Cherief-Abdellatif and Lugosi in their book, but the general formula is this one. So it is not based anymore as a convex, with the convex assumption, with the convex loss assumption, as I told you, kind of randomization kind of convexifies the problem already. But if you have a bounded loss, you have exactly this bounded, this regret bound, sorry, so it's almost the same as the previous one in the gradient descent case, but with some slight differences. The first one is that actually we do not simply consider the losses here, but the losses in expectation with respect to your strategy here. So with respect to EWA, here you consider actually the expectation of a strategy and you optimize over this. random strategy. And here there are small differences. So previously it was the bound B was replaced by the Lipschitz constant L. It was I think a constant of 2 instead of 8. And here clearly this, instead of having the KL divergence, which is divergence between distribution, you have like a Euclidean distance between parameters.
It's an elbow you have on the left hand side.
Yeah,
on the right hand side.
Exactly.
So you know the minimum in Q actually.
Yeah, exactly. Exactly. So the minimum of this is exactly the
Okay.
WA.
Okay. That's
So this is
okay.
Yeah, the minimizer on the right hand side is exactly EWA.
Yeah, sure.
And actually, if you want a small example, so to come back to the previous case, imagine that you have a finite number of predictors. If you tune the temperature parameter accordingly, you can recover this kind of bound that you have, like a square root of T bound in the case of a finite number of set. I did not say it, but if the prior here is uniform, so you have uniform weight.
So sorry, I'm lost.
Yeah.
So pi t is your EWA algorithm.
Yeah.
But the right hand side is the EWA, the inf on Q, you know?
Well, sorry,
So if you look at the infimum on Q,
where?
the stuff, so it's going to be given by EWA.
Yeah.
Okay, so you have the expression exactly after that? I'm just a bit confused by the way it's stated actually.
Yes, exactly. Actually, by definition, the minimizer of the right-hand side is EWA. Exactly.
Okay, so you work at that and that gives you the elbow for that. Okay.
Yeah.
Okay.
But the difference is that it's not. You will not consider here. I mean, it's the EWA, but at step capital T here. Capital T plus 1.
Yeah, that's the capital. Yeah, okay.
That's why you do not
Sure.
get the same.
Okay, that's the capital T. That's why. Okay. Sure.
And so this is the kind of inequalities that you can have. So the previous case, the realizable situation I presented in the beginning of the talk is very easy with you know that there is a true oracle and there are a lot of strong assumptions. Here without such a strong assumption, you still can have nice results as a regret bound actually. So now I just would like to present some results to show that how actually it is possible to go beyond convexity. Because typically the problem when you don't have convexity is that you do not have this inequality. This is exactly the definition of a convex function, which is that the loss is above its tangent, right? So if you don't have convexity, you don't have this. And as I told you, the convexity is the cornerstone of Bayesian inference, but the question is, if you consider like a non-convex function, such as, for instance, neural networks, is it still possible to get regret bounds? And what would be the order of the regret bounds? Because the typical, I remind that if you consider a convex loss, the typical order of the regret bound is square root of T. So would you obtain such kind of inequality? So the main problem in the proof, if you take a look at the proof, is that this inequality is not satisfied. So you cannot actually control your algorithm, the regret of your algorithm, due to the fact that you do not have this inequality. But actually, this is not a problem. I will just try to justify a bit why. So actually, to do so, we need to, so it's not really cheating, but we define a close notion of convexity, which is called near convexity. So a function is said to be nearly convex if it is not strictly convex, so if the function is not above its tangent, but almost, okay? So with a small difference of equal to epsilon, okay? And a result, so a result presented in the paper of so Shen et al., so I presented in the beginning of the talk, is that if you have not convex functions, but nearly convex function, with a near parameter equal to epsilon and Lipschitz function. So if you use the online gradient descent algorithm, you do not exactly recover a square root of T regret bound, but the regret bound is in square root of T plus epsilon times T. Okay. So what you see is that if you are able to to show that your loss function is not necessarily convex, but epsilon nearly convex with epsilon small enough, then you may be able to recover the regret bound that you had as if your function was convex. Okay. So to show this result, it is actually quite simple. So what the first thing we define is at step t, we define the tangent of the loss function LT when the tangent is taken at theta t, right? So this function is of course linear subconvex. Okay. So by definition of HT, if you apply online gradient descent to the sequence of function L1, L2, it's the same as H1, H2, H3 because the gradients are the same. So basically, the two algorithms are exactly the same. So if I apply online gradient descent to the sequence of loss function LT or the sequence of function HT, it's exactly the same. So what I am able to do now is to, as I know that HT are convex functions, I can directly apply the previous result. So if I use online gradient descent on HT, I exactly have this result, which is a straightforward application of the result I got in the previous section, right? Now, I just know that I have near convexity. So from near convexity of the function LT, I have this, okay? So this is just the definition of near convexity, and the beginning assumption was that my function is nearly convex. So what do I see now? That actually this quantity here on the right-hand side is equal to the opposite of this, okay? So it is equal to, so this term here, this quantity on the right-hand side is equal to LT of theta t minus HT of theta, okay? And what is LT of theta t equal to? It is equal to HT of theta t, because at theta t, the function is equal to the tangent. So this is exactly equal to HT of theta t minus HT of theta. So this is exactly equal to this minus this. So we exactly recover this, so which is the difference, so the sum of the cumulative differences is upper bounded by the cumulative differences of this, which is equal to this, plus epsilon times t. And we know that this is upper bounded by this, even this regret bound, so we exactly recover. So this is actually really straightforward. You just need to think about defining this convex tangent.
Do you have a good example of an epsilon convex function?
Yeah, we'll present the case of neural nets at the end.
Okay.
So actually, yeah. So what you see is that if you have an epsilon nearly convex functions, you have almost the same bound as if you were in the convex case. Sorry. And actually, so yeah, before talking about neural nets, just actually the argument that is behind and is shown in the paper is that your function will be epsilon nearly convex if your predictor is smooth. Actually, is smooth enough. This is exactly what I will just show. If you consider the spatial case of smooth predictors, so I directly formulate the prediction at step t as a function of theta, sorry, so that it's much more convenient to present.
Isn't that cheating by setting L also very small?
What is L?
You're gonna use like the upper bound on the gradient to control the convexity, right?
As well, yes, but I will. It's not something I will tune actually. I will just put a smoothness parameter on the predictor. I will just assume that the predictor is smooth, is very smooth. So it's like kind of a Lipschitz assumption on the gradients.
Okay.
And actually,
yeah. To make sure that epsilon is small, don't you need like the derivative? So the second derivative to be small.
Yeah, exactly.
But then by choosing that parameter to be small, you're also making the L. You know, in the L smooth.
Yeah.
Definition.
Oh yeah. I was sorry. Was it supposed to Lipschitz? Yeah.
So you're using like the largest eigenvalue of the Hessian to control the deviation from convexity. So you want that to be small. So you want like the second derivative to be tiny anywhere, to be tiny almost everywhere.
Yeah, kind of.
So you're almost saying that, you know, this thing is actually not almost convex, it's almost linear, really, because the second derivative is like 0, very close to 0.
Yeah, this is the idea, actually. This is the idea. This is the idea. But in the example they show in the paper, actually, they took, so they not only consider the case of two layers neural nets, but in the case of two-layer neural nets, they show that it really scales in 1 divided the square root of the width. So even if your network is
The second derivative.
So I will show this just after. So actually, yeah. So the idea is that so here we don't talk about convexity. If we had convexity, we would have this is larger than this, okay, without any integral remainder. But in general, you can formulate this kind of convexity inequality as an inequality, like a development of Taylor, with an integral remainder, okay? So once again, when the function is convex, this is positive, right? And the point is that we assume that the predictor are smooth, okay? So if the predictor are smooth, this exactly means this. So so I choose to call the smoothness parameter S, but you can call L. I mean, and this says that your gradient is Lipschitz. So this is the assumption we make on the predictors, okay? And given this assumption, we show that we have this inequality with the assumption that the predictors are smooth. So what we see is that if we are on a bounded parameter set, then we get the near convexity with the parameter S times the diameter, the square of the diameter divided by 2. So to show this is very simple. Actually, so we make, so this is actually direct, sorry. Actually, we just, we try to control this in absolute value. So the absolute value of this is upper bounded by the integral of the absolute value of this, which is itself controlled by the integral of the norm of this times the norm of this, okay? Given the smoothness, the norm of this difference is upper bounded by S times small s times the distance between theta and theta t, okay? So you have the integral between 0 and 1 of small s, which is the thing you integrate, which is in the integral, times the squared norm of theta minus theta t. That's it. Which when when you consider the integral is equal to exactly this. So as this is really small in absolute value, so this is larger than minus this quantity. So definitely you have this inequality quite, it's very straightforward. And the question is that we have shown that the predictor is nearly convex in a way. So the question is that we are not interested in the smooth predictor, but in the loss function. So we will see how we can transfer this near convexity from the predictor to the loss. And actually, we need basically two assumptions. So the first one is that the predictor is smooth, okay? The second one is that, so here, the loss function are convex and Lipschitz, but the convexity does not hold on the parameter theta, which was the point we didn't want. It holds on the parameter on the left, so on your prediction. So typically, you see that if you're in a regression framework, you have the convexity in F. This is not a problem. It does not, I mean, it's not a huge assumption. It's not the same as asking the convexity in theta, okay? So under these two assumptions, we exactly have this, which means that if the domain is bounded, you have the epsilon, the 2L prime S R squared near convexity of your loss function. And the proof, once again, is quite straightforward. So I just recall, so this result is exactly the same here, okay? So how do you prove that? So it is very easy to follow. So the first line, I just used the convexity of the loss function with respect to F, to the first argument. Then from this to this, I just wrote this as the Taylor development with integral remainder. Okay, so this is an equality. Then I developed this time this plus this time, sorry, this time this plus this time this. This is another equality. Okay. What I do I recognize here? This times this is just the derivative, the gradient of the loss function with respect to theta. Okay. So you just have this, okay, plus, so it's exactly the same thing as what is above. And what I know is that this, the loss function f is Lipschitz in f. The loss function is Lipschitz in f, is L prime Lipschitz in f, so I got this. This, I just saw that the remainder is lower bounded by this, or upper bounded in absolute value by this, so I get this. And this is just the first order part that I got in the convex assumption. So I exactly get this. And if I upper bound, so I see that if I bound the domain, so this shows that the loss function is nearly convex. So to sum up, I'm not sure it is stated like that in the paper, but this is the idea they use in the proof. Basically, if your loss functions are convex and Lipschitz, but in the first argument, none in the parameter theta, that your loss function are Lipschitz, so in theta this time, and your predictor are smooth, then you got the near convexity, and thus this can be formed. You can obtain the final regret bound, like for online gradient descent. So I state this for online gradient descent, but you can choose the algorithm of your choice and replace here this quantity by the regrets suffered by the algorithm of your choice in the convex case. Okay. So what can we see is that, so typically R is something that is fixed. Okay. L and S are fixed quantity as well in general, or maybe depending on the dimension of your space, but still. And the only quantity that is new here is the smoothness level. So if your function, the predictor function is smooth enough, this means that actually you will possibly be able to get rid of this term, or to show that this term is smaller than the square root of t, in which case you will come back to what we could call the convex regime. I don't know. Okay. And just a small example. So they consider the case of 2 layers neural networks in the paper. So they also consider the case of deep neural networks, but it's a much nicer result, I think. And so to present this result, so the way I wrote the function is not standard, but actually it's mainly used for the way they initialize the neural net. So actually the initialization scheme is as follows. So this is a 2 layers neural net. So theta are the weights from between the input layer and the hidden layer, and A are the weights between the input layer and the output, right? So the final weights are initialized and then fixed throughout training, right? And they initialize like that. So the first half of the weights are randomly initialized using a Rademacher, and then the other half is fixed as minus the first half. And the way they are initializing the input weights is that they actually still initialize the first half of the weights, and they're taking the second half as equal to the first one. So the reason why they're doing this is that what is convenient in their computations is that when they evaluate the loss function at θ1, it is equal to 0, actually. So it is more for convenience of their computations. It's not. I don't think it's like something that is very important, but it's the reason why they formulate it like that. But after, in the way you update your weights, you do not have to make this split into. It doesn't matter. It's really important in the way they initialize the neural net so that they can have convenient computations. And what they show is actually, so the assumption that they have is that, so they assume that the inputs have unit norm, okay, kind of a standard assumption, that the loss function is convex and Lipschitz in the first argument, so not a really strong assumption as well. So they make some smoothness assumption on the activation function. And what they have is the following result. So basically what they show is that the predictors, the neural network predictors that which I just defined, are actually 1 divided by the square root of m smooth, where m is actually the width of the hidden layer. So what they show here actually is that if your network is over parameterized enough, so if the width is large enough, so typically if the width is at least as small as the time horizon, then in a way you recover exactly the convex regime, and you got a square root of t we get found. So exactly the result that you get. And yes, so I had maybe a few more things to say, but I think it's maybe it will be a bit long. I'm not sure it's very important to say this. So this is mainly what I wanted to say.
Very useful. That's really cool, actually. It doesn't seem too complicated as either the technique. Right?
Yeah, the techniques are very the technique. Okay, actually, the idea was really to rely on the smoothness and to be able to control the remainder term, actually, just to say that you can control the remainder term, because when you don't have convexity, you need to control this remainder term, and you can control it using smoothness to transform the near convexity, the smoothness from the predictor to near convexity in the last function, which is actually, but the ideas are not very complicated. I mean, the technical part are not complicated, just computations.
Yeah.
It looks like you can apply this kind of stuff to bandits, actually. The whole bandits, but yeah. Interesting.
Do you need to have like
it's really worth
is
looking
there a
at.
way
It's
to
not too bad,
use,
but you've been looking at, I think, quite a bit.
use like somehow I feel
on
like
this
this
paper.
because
It's
you're
very
using the
interesting
ellipsis
online
function on the gradient.
Yeah.
And is there a way to
like
only apply
nice
like
big
in like small distances?
What you mean by a small distance?
So when you're writing down the equation where you don't have convexity,
Yeah.
so you use the smoothness to control it. You're essentially trying to control the change in the loss.
Yeah, you should. I think there's something
In the what? I did.
The change
Forget
in
about
the
your
change in
problem.
the
It
loss
is the
with the
standard
change in
problem
Z.
where you have.
Yeah, okay.
So
And,
do you have to control that over
I mean,
Z
people are
minus Z
sure
dash,
trying
like
to do
Z and Z dash being
because it's kind of
anything?
obvious you don't worry about
Can you
resolution
control it
or-
like in a localized manner? Could you get away with just controlling Z and Z dash being close, relatively close to each other?
I don't know. It's a good question.
So what did you say? Apologies, George.
No, you should pay attention.
I was talking to Amit.
Can you go back to the slide?
Sorry. Be grounded.
This one, yeah.
No pine food. Yeah, so there.
It's noon.
Right. So how do you apply this? Is there any way to control the distance between theta and theta t in the way you apply it, or do you have to apply it with theta and theta t being anything?
Yeah, that's a good question. Actually, so yeah, actually in the general technical proofs in convex optimization, you have like follow the regularized leader and the standard proof just for online gradient descent, which are two different proofs. And the proofs used for online gradient descent do not control at all the distances between theta and theta t. They always assume like boundedness assumptions. And it's the proof coming from follow the regularized leader that indeed, in a way, they relate the distance between theta and theta t in their proof. They control this by using a Lipschitz assumption and so on. But if you would use such techniques that actually it's not theta minus theta t, but they relate this to, they relate this quantity, you see, it's not just theta and theta t, but the dot product of theta and theta t and the gradient, they relate it to the distances like theta t minus theta t plus 1. And this is something that are able to control. But theta minus theta t just itself is a bit difficult to control. This is why, in general, we make general assumption over the.
So, I mean, my question is, will you be applying this inequality to general theta and theta t, or is there a way to control what thetas you would be applying it to so that you can maybe have a less strict requirement? Because I think like using essentially smoothness to control convexity is, it will only give you bounds that are, I don't know, like reasonable when the function is almost linear. Because you're essentially saying the gradient is almost constant. For the bound to be good, we need the function to be almost, sorry, not constant, the gradient will be constant, so the function will be almost linear. And so, okay, so maybe for like neural nets, if you're using ReLU or something like that, I can believe that in small scales, you build up with like linear parts. So that's fine. I'd be happy to believe that. But in large scales, that seems to be very restrictive. Like, you know, if you look far apart, like theta here and like theta at the other side of the room. So they should not be, I don't see any reason why the gradient shouldn't change much.
But isn't it because they do on top of that this other parameterized stuff? So you're in the neural tangent kind of stuff. So
yeah, but then why do you need to do that? That's complex anyways.
Actually, another point is that in their paper, actually they take into account that this scaling. I mean, what I hear by scaling parameter is this one. No, sorry, it's after. You know, this scaling parameter 1 divided by the square root of m, they play over this actually, and they show that actually the choice of 1 divided by the square root of m, I took this one, but in the paper they took a general value for this, and depending on this value, I mean, you do not get exactly this kind of result. And I mean the smoothness directly depends on the scale you choose for your network. So in a way, yeah, it's I mean, I wouldn't say artificial, but they choose the scaling, and they choose this one as well because I mean, they relate this with expressivity, because another thing that they are doing is that actually the main result is not exactly this one. Sorry, actually what they are comparing their cumulative loss to is not the best neural net. Is actually what they are doing is that they want to compare it to a competitor that is external to a neural network. So they are choosing their NTK, they are building the RKHS that is associated, and they are constructing the random feature space which is associated to the RKHS, and they compare this to the best function in the RKHS in the feature space. And they are saying that with this choice of scaling, the feature space associated with NTK is, I mean, can be very well approximated by a neural net. So the choice of the scaling.
That's a much weaker result then, if the infimum is only over this. So do I get the stuff? So they don't compare with the best neural net, it's just with the NTK stuff.
No, they do both. Actually, the first part is this one.
Okay.
Then they say that if you target the best random feature,
okay,
you have a neural net that is close to the best. I mean, the loss of the neural net, sorry, that is close to the loss of the best random feature to 1 divided by the square root of m distance, which is actually not even 1 divided by the square root of m, but the scaling divided by the square root of m. And they say that, so the upper bound this by the, I mean, I have the paper, I think I can directly show you this one. Yeah. So basically, yeah, they're showing this actually. You see, so they have the main result is this one. So they compare it. Okay, so their cumulative loss is upper bounded by the best network, okay, plus something that is square root of m divided by the choice of the scaling. Okay, plus 1 divided by the scaling, and they show that they can approximate, if here it is the best, whatever the random feature you choose, they can approximate it using a neural net plus b divided by m. And if your choice of the scaling is b in square root of m, so the scaling is like NCK regime, then you can reformulate it so that you get this main result that the state is this one. So this comes from the regret bound just formulated with the neural networks. And this is the an expressivity term.
Let's say you take a wide neural network that you're using in practical application.
Yeah.
What would L be? How would L scale?
In general, well, in theory, it would be the square root of m. So like the anti-K regime. What they say is that if they want to achieve like a trade-off between expressivity and good regret, and if you want to compare your strategy to the one of a random feature, which is a bit external to the function you choose, they say that the best thing to do would be to scale to choose the anti-K regime. But if you choose like a deep, even if you choose a deep neural network, the result is like a bit it's unclear. I think it's more unclear because if you take a look at the general regret for deep neural networks, which is this one from 3.2, actually, yeah, actually the fact is that the radius of the Frobenius norm of the weight is constant in the 2 layers neural net. So it means that you have like a 1 divided by square root of m move in each direction. But in the deep neural network, in order to have not vanishing bounds, they're forced to choose like a radius, which is kind of this order. So it is very, very small. The radius is very small in the number of, I mean, in the width. So actually, they artificially choose to choose a very, very small radius. I mean, quite small radius, so that they can obtain this kind of bounds. But they do not even recover the square root of t, the convex regime, because they have to, here h is the depth and m is the width. So in a general deep neural network, I think that the question is, the answer is unclear.
And d is the dimension.
No, d is the small d is the dimension is p, the input dimension, and d here it's the because they can allow for multi-class, not multi-class, but not only one output. So for multi-output, so multi-dimensional output. So d is the dimension.
So it's only logarithmic in the dimension.
Well, not necessarily. I mean, it will depend on the Lipschitz constant that you use and the.
Okay. Yeah, sure. Yeah. So L is probably hiding some.
Yeah, some dimension, two-dimension dependent.
Can you go up? Who are the authors?
Yeah, it's like Chen, Edgar Minasian, Jason Lee, and Hazen.
Thank you, Badr. It was very nice. Someone asked question online. We didn't check.
It's what I was. Thanks. Just a thing.